Hello students, so welcome to this lecture on the RC approximation and then the delay estimation for the CMOS circuits. So in this particular lecture, we will see how do we model or approximate a transistor into an RC circuit. So before that, going into that level, we need to understand why is that the modeling very essential. In a sense that if you use the transistor itself, in our case of an inverter, a very primitive digital circuit, what is that the delay or the performance values, and what kind of what kind of estimation methods we have to employ so as to reach to that particular the delay parameters. And to be very specific, it will be the propagation delay, the parameters. And once we calculate that, how do we then model it appropriately into an RC circuit? So that's what we are going to learn in this particular lecture. So moving ahead, so we want to calculate the propagation delay, especially the falling one, because we are again using the inverter where the NMOS transistor is operating in either linear or saturation region, for which makes the output voltage to discharge to zero. So we are once again calculating the propagation delay falling for the same inverter circuit, but now we are using a different current model. We are using a short channel current model. Now remember that in a short channel current model, the VDS saturation is a combination of the pinch off as well as the velocity saturated region. Right, so what it means is it's a combination. It's basically what we had said earlier. It's nothing but equivalent to a parallel combination of the pinch-off region and the velocity saturated region. Right, so VDS saturation value for a short channel model turns out to be the critical voltage where the velocity has saturated multiplied by the pinch-off region where it is VGS minus VT, and then divided by VGS minus VT plus VC. So this VDS saturation value, and we had seen this earlier also, the VDS saturation value estimated from the short channel current model turns out to be actually less than the 0.7 volts, right? VGS minus VT for an inverter circuit where the inverter input is 1 volts or the VDD value turns out to be nothing but 0.7. But VC value, it is around 1.04 as we had seen last time. So if I do a parallel combination of 1.04 and 0.7 volts, I will get actually 0.411 volts, right? Which is very, very far. I mean, what it means is it is far less than that of the 0.7 volts. So if I actually draw an axis here, right? If I draw a time axis here, and let's say that this is my output voltage of the NMOS transistor in the inverter circuit, where the NMOS transistor is used in the inverter circuit, while it actually drops in the long channel model. We had got two profiles: a linear profile, linearly decreasing profile, output voltage profile I'm talking about. It is a linearly decreasing profile, and then exponentially decreasing profile, right? In this particular case, right, so we have some kind of a profile and then another profile. This, in the long channel model, this point was 0.7 volts. But here it will be 0.411 volts starting from 1 volt. Right? So if the output node voltage is charged to 1 volts, that means the inverter, the input to the inverter was 0 volts, the output was 1 volts. And then the step input of 1 volt is applied at the input side. That is when the output voltage will start decreasing. So when the output voltage is 1 volts, we know that we will be able to analyze that the transistor, NMOS transistor, will be in saturation. Whenever the output voltage is somewhere here, we know that the output voltage is above 0.411 volts. So the NMOS transistor is in saturation. Till it reaches 0.411 volts, the NMOS transistor will be in saturation. So I'm going to write this as NMOS is in saturation. Which is, in a way, it is good, because if I want to calculate the propagation delay falling, I don't have to go below this 0.411 volts, right? So the propagation delay falling, the voltage point to estimate the propagation delay falling is actually somewhere at 0.5. So I have to reach somewhere here, and then this particular point will be the propagation delay falling. Right, so this point will be my 0.5 volts. So that particular point on the voltage axis is 0.5 volts, and that particular point on the time axis is actually propagation delay falling. Right, hope this is clear. So what it means is, in the long channel current model, while I was actually doing a transient analysis of the inverter circuit, we have to estimate the T saturation point, and from the T saturation point we used to get the value of TPDF. Here in the short channel current model, right, there is no need to calculate the T saturation point, because the T saturation point is way beyond the TPDF point, right? So if I want to find out the TPDF value, I can actually use this particular, the NMOS, which is in saturation region, use that particular current, equate it to the capacitor discharging current equation, and then I should be able to do the integration and then find out the TPDF value. So that's what I have done here. So till VDS from 1 volts, VDS or V out, it's the same thing, because in an inverter circuit, we know that PMOS and NMOS, if I draw this is my VDD value. This is my PMOS connected to the NMOS, right? So this is my NMOS value. And then this is my V out, which is nothing but the VDS value, drain and then the source, right? So till VDS is greater than 0.411 volts, NMOS is in saturation. So I'll equate the IDS saturation current equation, which is nothing but WC oxide, velocity saturation, multiplied by VGS minus VT the whole square divided by VGS minus VT plus VC, is nothing but equal to the discharging capacitor discharging current equation, which is nothing but C load dV out by dt. If I do the integration on both the sides and take out this dV out on one side and then dt on the other side, right, I should be able to find the solution, find the expression for V out. So that's what I have done here. So V out with the limits of VDD and V out, and so everything else, all the parameters which are constant will come outside. Velocity saturation is a constant, VDD minus VT plus VC is a constant, VC is anyways a constant for the particular VGS value. So it will come outside, and then WC oxide, VDD minus VT is anyways a constant value, so it will come outside. So what remains is nothing but the dt parameter, which after the integration will give us the t value from 0 to t, and this one will be VDD to V out. So the limits here as I've taken, so because it starts, the initial condition is, the output voltage is VDD when the time is equal to 0. And then it reaches to, till 0.411 volts, we will consider this to be a V out of t for the time domain t, right? So, this is nothing but whatever is written here. So this particular component is what I have written here with the minus sign, and this continues here with the t. So on this side, on the left hand side, it is nothing but V out minus of VDD, but there is a minus sign which is gone here and makes it VDD minus V out. So finally we have a V out here, which is nothing but which comes here on the right hand side, and then this one will go to the left hand side, and we'll get V out of t is equal to VDD minus of this whole expression of WC oxide, VDD minus VT the whole square, velocity saturation, and all those things. Right, and if I put V out is equal to VDD by 2, that particular time instance will be the propagation delay falling. So that's what we get. If I put V out is equal to VDD by 2, the time instance is nothing but TPDF. Right, and to make it very, very clear, right, so this particular expression, or rather, if I look into this particular expression, V out is equal to VDD minus the constant values into t, what it says is, it is a linearly decreasing profile with respect to the time, right? Linearly decreasing profile, right? So with respect to the time, it is a linearly decreasing profile. So there is no exponential profile here. We will need to calculate the propagation delay falling, because the propagation delay falling is the point where the output voltage decreases to 0.5, and VDS value, the saturation value in the short channel current model, is well within that 0.5 volts. So the NMOS transistor is still in the saturation region, it changes from saturation to the linear region only at 0.411 volts, right? So no need to get the exponential profile in the short channel current model to calculate the propagation delay falling. All right, hope this is clear. So moving forward, so this is what the expression we have for the propagation delay falling for the short channel, if you are using the short channel model, and taking the same parameters of width of 1 micron and capacitive load of 20 femtofarads, we get the propagation delay falling in the short channel as 10.79 picoseconds, right? And if you remember, the propagation delay falling using the long channel model was somewhere around 7.79 or 72 picoseconds. So this one is 10.79 picoseconds. And it is to some extent intuitively what it says is the short channel current model takes a little bit more amount of time for the capacitive load to discharge till 0.5 volts as compared to the long channel current, which is in a way it is it is intuitively correct, which also signifies or reiterates that the long channel current, which is an ideal current, is always always gives the higher values for the same VGS value or for the same VDS value. It gives a slightly higher values as compared to the short channel current model. And the reasons are, we had seen earlier, that it is due to the mobility degradation and the velocity saturation effect, where for the same VDS value and the same VGS value, we will get the current to be lesser. And because the current is lesser, the discharging current is actually less. So the discharging rate with respect to time is also less, and thereby the capacitor takes more time to discharge from 1 volts to 0.5 volts. All right. Hope this is clear. So up till now, what we had seen was the long channel current model and then the short channel current model, and then giving the propagation delay falling of some values of 10.7. So let me go back and then see that 10.79 picoseconds, and then the long channel current model gave us a value of somewhere around 7.72 picoseconds. So what if I take just an RC circuit? The C value is, let me pick up the pointer. The C value is the same as what we had taken earlier, the 20 femtofarads. And this R value, I'm just taking a very simple value of 1 kilo ohms. And let's say that a step input of VDD value is applied, and then the capacitor starts charging. All right. Although, if I want to really estimate the propagation delay falling, the capacitor should be discharging. But yeah, nevertheless, I think even for the, if I use the same R and C values, the propagation delay falling and then the propagation delay rising will be the same. Right. So for the charging one, the capacitor charging profile is nothing but VDD into 1 minus e raised to minus t by RC. And if I want to find out, let me draw the profile, and then we'll see that what should be that point. So this is the particular exponential profile, and this is the time constant where it reaches to the 63% of the VDD, the maximum value. In this case, the input voltage applied is VDD, right? And then this particular time axis, we will get tau, which is a time constant. Time constant is the instance where the output voltage or the capacitor voltage reaches to the 63.3%. But what we need is actually the 50%, right? The 50% point where the capacitor voltage reaches this particular value is what we need, the 50% of the capacitor voltage. So this particular point on the time axis is what we will say that this is propagation delay rising. And if I use the same R and C values, it will be nothing but the propagation delay falling. Right. So although in this particular equation, this is the capacitor equation, and the discharging profile will also be the very similar. So I'll write the discharging profile once it is completely charged to VDD. The discharging profile will be nothing but VDD, and then we will have e raised to minus t by RC. So this will be the discharging profile, and from the discharging profile, we should be able to calculate the propagation delay falling. right? So in this particular equation, in this particular charging profile equation, if I put the capacitor voltage as VDD by 2, right, this particular time axis will be the propagation delay rising, right? Although I've written is the propagation delay falling, what I'm assuming that taking the same RNC values, it will be nothing but the propagation delay falling and the propagation delay rising will be equal. So you can take one of them. So this particular parameter, if I put the values here, so this VDD and then this VDD gets cancelled, and then we will be left with exponential is equal to 1 by 2. So to remove this exponential, we will take the log on both the sides, and we will get log of 2 into RC as of my propagation delay falling or rising. That is when the output voltage will rise to 0.5 volts or it will decrease to 0.5 volts. Right, so log of 2 is nothing but 0.693 into RC. So if I choose the RC value as 1 kilo ohms, so sorry, this is 1 kilo ohms and 20 femtofarads, turns out to be 13.86 picoseconds. The short channel model gave us somewhere around 10 if I go back, 10.79 picoseconds, and the long channel model gave us somewhere around 7.72 picoseconds. If I take a simple RC circuit of 1 kilo ohms and then the same capacitance of 20 femtofarads, I'm getting 13.86 picoseconds. So what do we conclude here? So 10.79 is what I'm getting from the short channel. RC circuit is giving me 13.86 picoseconds. So what we are saying is, if we can model a transistor, if I can model a circuit, in the previous case it was an inverter which was actually discharging from VDD to 0, if we can model that into an RC equivalent circuit, right? And then if we can model into an RC equivalent circuit, then finding out the propagation delay for an RC circuit is much simpler than calculating it for a transistor, right? Because then in a transistor, I'll have to write the current equations, and then for getting the voltage expressions, I have to do the integration of that, and then find out the particular regions of the transistors, and then put the value of the VDD by 2 so as to find out the propagation delay, whether it is falling or rising. Right, so instead of that, if I have an RC equivalent circuit where the C is nothing but the load capacitance, so if I can find out an R value, equivalent R value for a transistor, whether it is charging or discharging, if we can somehow find out an equivalent R circuit, then it becomes much easier for us to calculate the RC, the propagation delay falling or propagation delay rising. So the performance of the circuit, if we can make that circuit, or if we can approximate that circuit into a series of RC circuits, right, for a larger digital circuit, CMOS digital circuits, if we can approximate into a series of an RC circuits, then it becomes much easier for us to calculate or estimate the performance or the delay parameters, right? And one more thing, so this one was 13.86 we got because we had taken log of 2 into R into C, right? So this log 2 component is kind of applicable when the input is a step input, when the input going to the circuit or the inverter or the digital circuit is a step input, right? So this input is a step input. Generally what happens is if we have a step input given to an inverter, the output of the inverter is actually cascaded to the other stages, and then so on and so on. So in a millions and billions of transistors or the inverter circuits which is used to design a system, we will never have this kind of a step input applied to the another circuit. So the output of the very first circuit will be a in this particular case we have a ramp and then the exponential profile. So this particular the input profile is never a step input for the subsequent circuits, for the subsequently cascaded circuits. So it is always some kind of a linear profile or an exponential profile which goes as an input to the next circuit. So in that case, to make a conservative approach, we take out this log of 2. The reason is very simple, right? If the input is not a step input, if it is something else, my delay, the output of the circuit for which this particular input is given, right, will be further delayed. So in that circuit, in that case, to keep it very simple yet a conservative approach, we will remove this log of 2. That means we will the 69.3% of the RC, we will remove it. So we'll take it the 100% of the RC value, right? So for an input voltage which has a ramp, the output voltage, the delay estimation, we'll consider it to be a product of R and C. Right, so that's what I've written here. For conservative approach, delay is considered to be an RC value to accommodate for the ramp input, right, or the ramp input, and not for the step input. So we'll not have a step input always. So since the capacitor is 20 femtofarads in both the case, short channel and RC model, R needs to be estimated. So that's what we want. We need to estimate an R, and R is considered, right? So if you look into the R value, it is considered as a switching resistance of the transistor. So what we are saying is, so we will use the same capacitive load. We'll use whatever is the capacitive load, 20 femtofarads or 10 femtofarads, whatever it is given. The transistor now, based on its operating region, we will call it, we will use the switching resistance of the transistors, whether it is a PMOS or an NMOS transistors, and use it to accommodate or incorporate in our delay model. So if I have a switching resistance, right, so we will use this switching resistance and then the capacitance, and then use it to either charge or discharge, and then find out the propagation delay falling or rising. So if the switching resistance, if determined, simplifies the estimation of delay and avoids the integral process, which tends to become more complex for the larger circuits, right? So hopefully you have understood this. It is quite clear. So what we really want is from here on is finding out a switching resistance of the transistors which are used in the circuits. Maybe it is an inverter circuit or any other digital circuit. Find out the switching resistance and use the switching resistance along with the load, whatever is the equivalent capacitive load capacitances associated with the output node voltage. Use that, form a RC circuit, and then estimate the propagation delay falling or rising for that particular equivalent circuit, so as to make it becomes a very simplified process.